everyone. Good morning. Welcome to the second talk of the day in this track, where we're going to introduce you Rajomon, our design for microservice overload control system. This is a joint work with me, Akis, Paul, Shuyue, Justin, Henri, Konstantinos, and Ben Lee. We're from UPenn Distributed System Lab. Our Konstantinos is already an AP in UCLA. Okay, first, let's start with what is microservices and why do we care about the overload. Microservices is a cloud application paradigm as opposed to the traditional monolithic applications, where microservices breaks down a huge cloud application into smaller pieces, hand over to different teams for faster development and easier maintenance. It is more modular, scalable, and that's why it has been long adapted by those large tech companies like Twitter, Meta, Netflix, Google, Amazon, Alibaba, etc. It has also been very popular outside of IT companies, according to another Software AG survey at 2021. Approximately 75 to 85% of the IT decision makers use microservices, even if they are retail, finance, or public sectors. So, okay, cool. Okay, now we're running our cloud application in microservices. That's great. What's next? We want to make our user happy. And for interactive applications, that means we want to serve a lot of requests with low latency. And that's what I mean by performance stability. We learned that performance stability is crucial from various reports, and it's important for our business. You're gonna lose half of your visitors if your page takes more than 2 seconds to load, according to Acme. And from another report, we know 0.1 second delay of your shopping or online shopping platform can reduce your average order value by 9%. And that's why companies have adapted service level objectives to specify the request latency for their service. However, performance stability doesn't come for free, and it largely depends on the incoming load. And sometimes the load could surprise you. Like when Taylor Swift released the Midnight album, during midnight, too many users waiting to listen actually crashed Spotify service. How did that happen? So this is a simple experiment of the hotel reservation application we developed. On the x-axis is the time, and on the y-axis is the demand. So for the first 5 seconds, the demand is kind of mild at 4,000 requests per second. The system can handle it pretty well in green as good put. By good put, I mean requests are processed within the target. We count it as good put. But after the demand jumped from 4K to 10K RPS at 5th second, all requests turn to red, which is SL violation. So they basically doesn't meet the latency target anymore. Even worse, after 3 seconds, the system is down. And that's exactly what we want to avoid. That's why we need overload control for those cloud applications. Well, at least we want to keep serving the 4K RPS, even under heavy load. And that's the purpose of this overload control. It sounds easy, but actually not. I'm going to talk about the challenges, starting from the characteristics of the microservices, 3 of them. First, decentralization. So microservices are decentralized, by which I mean each microservices only knows their own stuff and need to make their own decisions. There's no single entity has visibility or ownership of the whole of other microservices in real time. And second is microservices are interdependent. So a request usually comes in and need to invoke many downstream services, waiting for responses to return. What's the implication is that now if you have a slow and overloaded service in the downstream, it's gonna cause the queue to build up on this call path and lead to cascading quality of service failures on this call path. And third, microservices are also multiplexed. According to Alibaba microservice trace released on 2022, about 90% of the call graphs involves services that are also shared by other call graphs. So each service provides multiple APIs interfaces that goes to different downstreams. the implication is that now if you have one type of request that involves overloaded service, like type B, it could overload the shared services and cause a head-of-line blocking to a not overloaded interface, type A, in this example. That's why it's challenging, because you need to figure out which interface actually involves the hotspot. Okay, from the challenges, we can derive 4 control desiderata to handle these different challenges. First is decentralization, by which I mean we don't want services to be blocked by any centralized decisions and waiting for the communication to come before take actions. That could cause delay. And second is end-to-end server-side coordination. When we take actions to control the overload, we want services to be aware of the downstream congestion level of the downstream services, because at the end, they need to collaboratively serve the request. And third is relimiting. As we want to reduce the rate in order to handle overload, the earlier is the better. And the earliest is to do it at client side, because if client can reduce the rate just perfectly, then we actually don't wasting computations, dropping requests deep down in the call graph. And fourth is interface granularity. This is kind of intuitive that when we take control actions, we want to be mindful and aware of which interface are we controlling. At the end, they are not involving the same services. Okay, and there has been quite a lot of work in this domain. I can list them in this chart. First is Dagger. It was an early load shedding mechanism that runs on every single microservices and dropping requests based on their interface, based on the priority of their interfaces. And we have Breakwater, which is a receiver-driven, credit-based, fast relimiting enabled at the front end, sending credits to clients to relimit clients. It only runs the front end, and if we extend it to everywhere in the call graph, that's our extension. We call it Breakwater D. And we also have a recent paper that used top-down method with machine learning-based approach at the front end to drop request, but takes consideration of the end-to-end metrics. And we have our paper that satisfies all 4 control desiderata. Hopefully I can convince you with the following slides. So what is Rajomon? As we promised, is a decentralized over control that is aware of call graph dependencies and request interfaces. How do we do that? We're gonna use the 2 building blocks, tokens and prices. Not surprisingly, tokens. Yeah, and then we're gonna talk about the mechanism to detect and control overload and some tunable, flexible policies that you can play around. So first, what are the building blocks of Rajomon? We use tokens. We ask clients to spend tokens on request. So they need to put tokens on the request, and then the token go along with the request throughout the graph. And we ask services to set the price on different interfaces and charge the incoming request the price. It's like a supply chain. I will talk more about how this works by showing you the mechanism. And while I talk about the mechanism, I'm going to use this social network, simple social network application as a demonstration. So first, how do we detect overload? Rajomon runs on every single microservices. It monitors the local queuing delay. Up to your implementation, queue could be thread queue. For us, it's a Go routine queue because we implement in Go. But anyway, you have a queue, and you can monitor it locally, the queuing delay. And when the queuing delay surpasses your target, we ask the service to increase its price. So now home timeline has a queuing delay that is beyond the desired level. And we have price increase. And what makes more sense is now we piggyback the price on responses and send it to upstream, informing front-end and even clients. Okay, and then now everyone knows the price, and we can ready to take any control actions. We have 2 sides of actions. First is relimiting, and second is load shedding. For relimiting, as I mentioned, client need to attach token to request. Now say this client has 30 tokens, and attach 20 to the request. Now it has only 10 left in its token pool. It's going to wait and limit itself and back off. This is how relimiting mechanism works. And on the server side, as requests come with tokens, server is going to check if the request has enough tokens or not compared to the prices. And it's going to drop the request if it doesn't. And it could happen anywhere in the graph because home timeline might have just increased the price again, and then it could drop more requests at this right in front of the home timeline. And as we promised, prices are distinguish different interfaces. So home timeline could be more expensive than user timeline, and then you would drop the home timeline request even though it has the same token with the user timeline. So that's how load shedding works in Rajomon. And we have also provided some tunable policies. So at this point, you may ask, okay, client, what if they send the same amount of tokens? We actually try to avoid that even if they have token generated at same speed, but we ask them to generate at different time and spend a random number plus the price. So it would look like 22, 24 times like this, so the threshold could still work. And you all may also question how is price determined. We proportionally update the price based on the queuing delay. So the larger queuing delay increase, the larger prices increase. That allows us to respond significantly and fast enough. And we aggregated price to the final interfaces, aggregate the price of each service to the price of the final interfaces, because at the end, the request is about interfaces, not about services. I don't really have a lot of time, so I'm going to skip this, how prices are aggregated. If you are curious, please check out our full paper. We actually evaluated Rajomon extensively with 4 baselines on 3 different applications and multiple interfaces. I'm just going to show you a small subset of the experiment to see how it actually works out for with and without the ghost control desiderata. So on the first is, again, the similar figure. You have x as time, y as the demand. If the request is served timely, it's green. Otherwise, it's red. And it could be dropped as yellow, and it could be relimited in light blue. So Rajomon transitions smoothly from the warm-up 5-second period to the 5K RPS during the overload period, whereas the centralized top 4 would suffer from this period of service unavailability because the delayed reactions from the centralized bottleneck. And if we add another baseline to the same setup of, I forgot to mention, this is, again, the hotel reservation application, single interface, okay? And if we add another baseline dagger, we see a different implication. So both dagger and top 4 only dropping requests without relimiting clients. That's going to be expensive. See how Rajomon does is it first drop requests for the first 2 seconds and push the duty to clients to relimit themselves. That's going to save you computation. Well, Dagger actually has the same throughput at 5K RPS, but half of them actually are violating the SLOs because they extensively drop a lot of requests in the middle of the graph. That's not good. And another baseline of breakwater D, we see something different again. So breakwater D and Dagger both are running anywhere on the graph, but they don't have a coordination. What does that mean? You could suffer from a low throughput if you don't have the services agreeing on the admission rate. They actively shed loads, but they don't agree on the final load that they would serve. Whereas Rajomon actually have this coordination on this throughput. Okay, this is final slide. This shows the 4th desiderata, where Rajomon can actually handle multiple interfaces. This is a social network application with 3 different interfaces. After the 5th second, we added the 3rd column, compose post, which overloaded the system. But Rajomon can, as I promised, distinguish different interfaces and smoothly transitions from the previous state to the new state where it asks the 2nd column and the 3rd column to back off, whereas protecting the read user timeline from being affected at all and have a very smooth good throughput and latency. Okay, that's it. For more like line chart, please go check out our papers. I'm not going to show those figures right now. Just to conclude, microservices are challenging for overload control, and we tackle this problem with token prices and mechanism and policies. We implemented Rajomon as a lightweight gRPC library for easier adoption, and it has achieved low latency and high throughput. So I'm happy to take any questions.